In chapter 7, we take a bit of a departure from some of the mathy stuff that we've been doing. I mean, we spent some time in variance. We were looking at different ways to identify numerically what validity and reliability has been. And so we're going to depart from that a little bit and kind of spend a bit more time going back to the concepts of statistics, and in particular, kind of retrace our steps a bit to the beginning of the course and answer the question, well, if statistics can't prove things, what exactly can they disprove, right? Because that's how statistics work, and this is what chapter 7 gets at. You know, chapter 7, we kind of go back to what the researcher is trying to do with their research hypothesis or educated guess as to what their experimental outcomes are going to be. And then from those outcomes, right, you kind of apply them to the population. That's inference. But statistics can't prove that, right? They have to disprove something. And so research, chapter 7 gets into this whole aspect of what it is we set up to disprove so that we can, with a certain degree of confidence, say that our educated guess or research hypothesis is really the case, really is the state of the world. And the thing that we set up to disprove is something called a null hypothesis. And so this section here is non-mathy, and we kind of play around with these terms a bit, and hopefully we can structure again or revisit a framework for you in terms of how statistics work. And chapter 7 really is a preamble to chapter 8 and chapter 9, where we take this a little bit further and we get into the concepts of probability, and we ask questions, or what are the chances if I actually reject this null hypothesis and accept my research hypothesis? What are the chances that I got it right? You know, can I make mistakes along the way? But that's coming up a little bit later on. So here we go in chapter 7, and I hope it makes sense. So I've boiled the learning goals down to 3 for chapter 7. And so here they are. So we're going to distinguish between what we call the research hypothesis and what is called the null hypothesis. Now, these terms really are also part of research methodology. And so, you know, again, the color's kind of bleeding over from research methodology into data analysis. But that's okay. You know, if you've ever done watercolor painting before, if you put too much water on the paper ahead of time and drop in your color, you notice that the colors will often spread and mix. So that's what's happening here, and hopefully the portrait will be rather lovely when we're done. But that's what we're going to do. And then I want you to understand that researchers use statistics to disprove the null hypothesis. Now, we talked before at the beginning of the term that statistics disprove things. Well, I've already given that away here. Sorry, I've given you the ending of the entire story. Here it is. This is it. We should just pack it up and go home. If I was smart, I'd just stop at this slide. But I'm not that smart. We do have to cover these things. But that's what we do. Right? Researchers use statistics to disprove the null hypothesis, and we're going to unpack that. And the third part of the learning objectives is this. If you can understand that we disprove the null hypothesis, whatever that is, and we're going to get to that, that means that you've got to accept something else. And generally what that means is you're going to accept the original research hypothesis, because that's kind of what is left over. So this is how statistics works. Now, we just have to kind of put in these new terms, research hypothesis and null hypothesis. Later on in chapter 9, we get into some funnier things that are related to these two hypotheses, and those are called type 1 and type 2 errors. But for now, let's just get some definitions down. So what is a research hypothesis? Well, in its short form, a research hypothesis could be an educated guess. It's kind of what we kind of say it more. It's more of a softer way of saying a research hypothesis. It's an educated guess of what is going to happen or a potential outcome of an experiment. But the emphasis there is on the educated. Okay, these research questions or these research hypotheses are not postulated lightly. They stem from a wealth and a mountain of literature searching, right? And a lot of times these research hypotheses are original, right? Here is a research hypothesis or research question that has not been explored yet, and that goes through mining tons of ore, if you want to use that example, in the literature. right? And so we might believe that X causes a change in Y. And sometimes those are original questions. But another thing that happens in research that is often not discussed, and I think it's kind of important, is that sometimes these research hypotheses might not be original, but they might be similar to the original. They're not original, but they might be similar to someone else's research hypothesis. And so you want to duplicate or replicate that finding. So here in my example, we might believe that X causes a change in Y, and we go and run that experiment, and we have a particular finding, and we make a conclusion about that. Someone else comes along and says, you know what, I want to see if I actually get the same thing. So they do something very similar to us. They take our research hypothesis, they might adjust it ever so slightly, they run the experiment again, and sure enough, they actually get the same finding. And do you know what that is? We call that validation. That's actually an example of concurrent validation in a research setting. We finished covering concurrent validation in Chapter 6, where I'm using two different ways to come up with, to measure the same thing. And we can do that with research. If I run two similar hypotheses, and they might be slightly different. Maybe I've changed the sample characteristics a bit. Instead of using adolescents, now I've got middle-aged folks, for example. But I run a similar experiment and I come up with the same findings. What that means is I've actually validated previous research, and that is now added in towards building a stronger theory. And that's how research works. A lot of times the replication studies don't happen in research, right? This becomes a bit of a problem. But anyway, so what we do is we find a problem in our field. We come up with a research question. Then we run a research hypothesis. And the research hypothesis then translates this research question into a form that can actually be tested. So you can't just simply say, well, here's our hypothesis, here's our findings. You actually have to test something, right? We call it, in this case, we call it empirical testing because we use numbers. And so this is what we do. We gather measures, and from those measures we have numbers. We run those numbers in through our statistical packages. And then we kind of come back and we take those values and we come back and we actually answer the research question. That's how this works, okay? A lot of hypotheses kind of come together with two different things in a sense. I've had three on here, but really it's the first two. And these hypotheses come out in two different forms. Number one, a lot of times we want to see if there are relationships between variables. So for example, later on in the term, we take a look at the relationship between height and weight. There's something about those two variables. They're very different. They're two different measures, but they relate to one another. There's some level of connection between those two variables. A lot of times, if I've got the measure of one variable, I can actually measure the outcome of a different variable based upon their relationship. It's kind of weird. It's actually kind of hard to explain sometimes. The second one is differences between population groups. This one's a little bit easier to understand with research hypotheses. I'm going to expect some change in a variable, whether it moves up or whether it moves down. I'm going to have some level of expectation. A lot of times we do that by comparing two groups together or many groups against each other. We can do that. And so this is what we mean by differences. Part of that is the effective treatments. Sometimes that falls, I'm not sure why I have that one on there, I'm sorry. I think that's just something that we understand. You know, if I get a boo-boo on my elbow, for example, my elbow is hurting, I'm going to take some ibuprofen to reduce the pain. That would be the effect of the treatment on pain. Pain would be the pre and post difference before I took the ibuprofen and after I took the ibuprofen. But you can even see the effective treatments on relationships between variables as well. And I guess I brought in treatments because very often that is the thing that the researcher can manipulate. It's the thing that the researcher thinks will cause a change in the variables that they're interested in. In my case, it might be I want to reduce Mike Bodner's boo-boo elbow pain. So I'm going to give him 200 milligrams of ibuprofen and see over time, maybe in 4 hours, his pain will be reduced. So I measure his pain before the administration of ibuprofen and afterwards, and we try and see a difference. When I teach statistics in this course, I focus mostly on differences when we start getting into the normal curve and probability because it's a little bit easier to understand. But know that a lot of research focuses in on relationships. We see that specifically in psychology and sociology, and also in medicine as well, and in nursing. And so I covered that last at the end of the term. That's chapter 5 and I think it's chapter 15 or 16, we get into that. So we can break the research hypothesis down into two different types. And the first one is a directional research hypothesis. This is the one that you see in most journal articles, okay? And this is where the researcher or the researchers come together and they pretty much have an idea of what they think is going to occur, right? And they might describe it in particular ways. They might describe it particularly or specifically. We're going to see this variable rise if we do this, and they might call that a difference type of hypothesis. Or they might do some sort of descriptive research where they collect a bunch of data together at once and then begin to take a look at how these variables that they've measured relate to one another. So they might predict a relationship or what we call an association variable. And so these are the two types. Again, the basic part of a directional research hypothesis is they kind of state what they think they're going to find. They have an idea. Are they right? Who knows? But that's what they think. The second type, and this is what you don't see very often, is what we call a non-directional hypothesis. And this is where the researcher thinks that there's going to be a difference or an association, but they don't know which direction it's going to be. Okay, so they don't know whether the direction, if it's a difference score between two means, one mean and the second mean, they don't know if the second mean score is going to go into the positive direction or the negative direction. Is it going to be higher than the original mean, or is it going to be lower than the original mean? They simply don't know. And part of that has to do, and you might ask the question, well, if they've done all the literature searching, they've done all the reading, why can't they come out and actually state what they think is going to happen? And sometimes what researchers find when they mine through all that literature ore is they find that there's a lot of equivocation in studies. What I mean by that is half the studies might show an increase in the second mean or a positive direction. The other studies show a negative direction. And they might be evenly balanced or close to evenly balanced. And so there's some, what I call it's equivocation. No one is really sure. And so researchers come along and they go along the same track of those research questions. They might adjust their study a little bit. They might improve on a measure, for example, or have a larger sample size to strengthen the robustness of the measures, to strengthen their confidence. And then they run their study. But they have to say at the beginning, yeah, you know what, we're not sure how this is going to go because pretty much everybody else isn't sure. There's a lot of equivocation with the findings. So let's put together here some symbology again. I'm sorry about the new symbology, but here we go. So the research hypothesis is often expressed as a capital H with a small subscript 1. And not just the research hypothesis, the type of research hypothesis. So it's going to be directional. Okay, and the researcher will often state the direction. So here's an example. They may say that, well, I think that the mean 1 that I'm going to measure at the beginning is going to be larger than the mean 2 that I measure later on. That's my direction. The first mean is going to be larger than the second mean. Or they could say the opposite. Well, I actually think that the second mean is going to be larger than the first mean when we run the experiment. But the thing we talk about H1 and H subscript 0. You'll see it in the textbook. And this is what these things mean. Okay. I think that's all I have to say about that slide. So the directional aspect and symbology. So the symbology for the non-directional hypothesis is a little bit different. We still have an H1 because, again, the researcher is still hypothesizing something, right? But notice what we have here in the center. We don't have a greater sign or lesser sign. What we have is an unequal sign. Okay, so with a non-directional research hypothesis, we know that one of these means is going to be larger than the other. We just don't know which one it's going to be. This is why you've got an unequal sign here. And that's also why you don't have an equal sign in there. Okay, it's got to be an unequal sign. There it is down there. Because one of these things is going to be larger than the other. The researcher says, I'm just not sure which one it's going to be, but I think one of them will be. That's kind of, you kind of like, isn't that kind of backing out of that? No, you're not really backing out. It really is an unknown quantity, although you think there's going to be some change. Okay, you can't have an equal sign. It's got to be an unequal sign because they don't know which mean is going to be larger than the other. So we're going to transition into the null hypothesis now, and I kind of have something up there, statistics and the null hypothesis. Now this is a bit of a recall. Remember at the beginning of the term, we said that we can't use statistics to show that something is true. It's much easier to show that a particular hypothesis or statement or something else is false. And so what we do in statistics is we do this. We set something up that we can use statistics to show that it's actually false. And if you can show whatever that is we've set up is false, if you can do this, then whatever is left over, likely that is true or likely that is the state of things. So the thing we set up to disprove is the null hypothesis. And you've probably gathered that by now from the previous slide. And so what a null hypothesis really is, it's a neutralized research hypothesis, right? In either research hypothesis, we said that we're going to find a difference between two means. Either one of them is going to be larger than the other, this is what we think is going to happen, or there's going to be a difference between two means, and we're not sure which one is going to be larger than the other. And so we nullify it, we neutralize it, and we say, in essence what we do is we come out and say, well, there's going to be no difference between the means, okay? That's what we do. And then we use statistics to actually disprove the null hypothesis. And if there is a difference left over, if we actually find this difference, in other words, whatever hasn't been disproved, this then is probably the true state of things. And so we might have, here's an example I have down below. What we end up saying is this: if there really was a difference noted between the two means, two sample means, it was likely due to something that we did, our intervention, rather than due to chance. Because chance is always something that is a certainty. Differences can happen by chance. And so we eliminate the chance factor, and anything that was left over, we say this was due to our intervention. This is probably the true state of things. Now, there's another layer to this, and that's the term statistical significance. As a matter of fact, the differences that we talk about are statistically significant differences or statistically significant associations. And there's some nuance to that we're going to add in some layers a little bit later on in Chapter 9. And so another way to express the null hypothesis, and again, here's our symbol. I probably should have put this on the previous slide. We see here that the symbol for the null hypothesis is an H with a subscript 0. That's our symbol. And so the null hypothesis is going to be, there's two things up here. I want to explain that. The null hypothesis up here, the H subscript O, mean 1 is going to be equal to mean 2. You'll see it expressed in the textbook as HO mu 1 equals mu 2. This is the population mean. Don't worry about that right now, because remember, we are doing inference. Remember, we go from sample to inference, and this is why we say we use the symbol for the population mean and not an X bar when we're explaining the null hypothesis. But it's still the same. Mean 1 is going to be equal to mean 2. And then we're actually use statistics to disprove that. And so the null hypothesis is the state of affairs that is accepted as true in the absence of any other information. What does that mean? It means that the only thing we know for certain is the null hypothesis is likely true. And then we use statistics to disprove that. That's what we do. It's a weird way of doing things. I apologize. It's kind of like going to a restaurant through the back door here. Why can't you just go and prove something? Well, you can't. It's not the way it works. We have to disprove something. Now again, it depends on how much is left over, right? So you have to have enough left over for you to say, yeah, there was a true difference. If there's not a lot left over, you might go, it's not enough, and that there was no difference between the two means. Okay, so to conclude here, until one can show that there is a difference between two sample means, I'm using differences as my example, One has to assume that there is no difference. That's the first assumption that you make going into a research experiment. If you're trying to use mathematics to disprove something, you assume at the beginning there's no difference between the means. Even though you think there's going to be a difference between the two means, you say, nope, there's no difference between the two means in terms of what we found here. And then you go and set out to disprove that. So let's take a look at this null hypothesis just a little bit further, because it is kind of murky here. When we run experiments, a lot of times you will actually see differences between two means, or you will see associations between two variables. Let's just look at differences now. That's the easier one to comprehend. And the question then becomes, is this difference that I see between two means because of something that the researcher did, or did this difference happen by chance? And in reality, there really is no difference between the means. The difference that I see there happened by chance. Okay? That's what could have caused the difference. Okay? Remember, we're working with samples here. Okay? A sample is from a population. So when I run an experiment, I might see a difference. And the first thing I have to say to myself is the difference that I saw here could have happened by chance. And in reality, in the population, these two things would be the same. That's the null hypothesis. So that's how the null hypothesis is linked in with chance. Okay? If I see a difference, the difference could have been caused simply by chance. And because I accept chance as that explanation at the beginning, that means there really was no differences between the means, because the difference I saw happened by chance. And so then we use statistics to disprove that the findings, the differences that we saw, happened by chance, right? Because in an experiment, as I have down below, let's say I've got a value of x and I apply it to a value of y and I expect a change in y. And when I do this, I actually see a change in y. That could have happened by chance. And I have to accept that, at least at the beginning, that what I saw here happened by chance until I can prove otherwise. And to show that something else caused this change in y, I have to disprove that it happened by chance. I have to disprove the null hypothesis. So the null hypothesis then provides a benchmark to see if any of the differences observed might be due to some other factor, right? In other words, if you can disprove the null hypothesis statistically, okay, we can then show that something else was responsible for the observed differences and not chance alone. And generally, that's what the researcher did in the experiment, right? We think that if we take this x and apply it to y, we're going to see a change in y. A change in y could have happened by chance. We're going to use statistics to disprove that, and that's going to allow us to go back and affirm our research hypothesis. We said x was going to cause a change in y. We disproved the fact that that couldn't happen by chance, and so therefore we've got to go back and say the only thing left over is our research hypothesis and what we did. That has to be the likely explanation. So this is how the null hypothesis works, and this is how we use statistics to actually prove something, but we do it through the back door by disproving the null hypothesis. At some point, we have to make a decision whether or not to reject this null hypothesis, right? And by virtue of rejecting the null hypothesis, we accept the alternative, which is the research hypothesis. But that kind of brings with it, a chance of error. And so we want to be pretty darn sure that we're making the correct decision. And so we have to kind of set what we call a threshold somewhere along the way where we say, okay, at what % chance do we think that the findings here actually happened by chance? And maybe it's 50%, maybe it's 40%. How low do you want to go before you say, the chances of the findings that we see here in our experiment, the chances that it happened by chance are so low, right? Maybe less than 1%, maybe less than 5%, as I have here on the slide. They're so low that, there's likely something else that really was the cause or the determinant of the effects that we see in our experiment. And so we cover this more in chapter 9. And so, there are certain thresholds that we set, and we'll get there. But this is what researchers have to do. And this is where this term statistical significance comes in. And this is where things began to kind of, this is where, George Costanza from Seinfeld, this is where worlds start colliding. We set thresholds for low levels of percentage, below which we say, yeah, that's a really, really small chance that the findings here happen by chance. And so it's a better route to go to accept the research hypothesis. And this is how statistics work. We actually do everything in reverse in statistics, right? In this case here, we set up the null hypothesis, and maybe the statistics show that we can actually tear it down. Maybe not. Maybe sometimes what happens is you have a null hypothesis, and it's like, well, yeah, there's a 50% chance here that the findings did happen by chance. 50-50? We're going to have to lean towards chance and not towards our research hypothesis. And so here we are finally at this term, statistical significance. Researchers love to throw this around. People do, right? Well, the findings were statistically significant, and they seem to carry some weight to them. And the weight is there for sure. And what statistical significance means is if we find a relationship or a relationship between two variables, or a difference in the mean between two variables, or we've constructed a model of explanation with several variables, what we're saying is the findings here that we saw that are statistically significant did not happen by chance. They actually happened due to some other kind of systemic influence, right? It was the drug that we used. It was the behavioral intervention that we used with these people that actually is responsible for these research findings, whatever those research findings are. That's what statistical significance means. If something is not statistically significant, and you'll see this in research papers, they'll say, we found no association between these two variables, or we found no significant differences were observed between, X, and Y. What they're telling you is, despite what the numbers say, and the numbers might be different, okay, the numbers might be different. You may take a look at them and go, what do you mean 30 and 35 aren't different? No, well, they are numerically different, but the cause of the difference really was due to chance. It wasn't due to our intervention. That's when things are not statistically significant. And so this is what this concept means, and it's an important concept for you to grasp. Okay, so let's summarize this section here. So researchers make hypotheses. They think that some things are going to occur, often based upon something that they do. We often call these things interventions. For example, the giving of drugs, behavioral applications, those types of things. And that the change that they see in the scores they're measuring are really caused by what they've done. Okay, but they can't prove that difference happened because of what they've done, right? At least they can't prove that using statistics. So what they do is they set up the null hypothesis. And the null hypothesis states that, well, there really is what we saw here really happened by chance, and there really is no difference between the means in reality. Like, just because you saw this change in your sample doesn't mean it's changing in your population, or it will change in your population. And so they set up this null hypothesis. So the null hypothesis says that there's no difference that you saw between the means in your study that was due to the intervention. In other words, any difference that you saw simply happened by chance. And that could even be a big difference sometimes, believe it or not. Sometimes with small sample sizes, you'll see these huge differences and you go, whoa, here we go, right? Yeah, then you've got to apply statistics. And so researchers use statistics to actually show that it wasn't chance that caused the difference. And so if you show that it's not chance, you can actually reject the null hypothesis. And we actually use the word reject. It's kind of a harsh term to use. So the researchers reject the null hypothesis. Translation: by using statistics, we've shown that there is no chance, or a very, very, very small chance, what we saw here actually happened by chance. We have to accept something else. We have to accept that something else caused this change or caused this difference that we saw. And so the rejection of the null hypothesis means that in all likelihood, what the researchers did, right, the intervention, the behavioral therapy, whatever it is they did, really caused the change in the variables that they saw, and that really is the true state of things. their experiment, for lack of better expression, worked. It didn't happen by chance. And when we say that there's these differences that didn't happen by chance, and when we see these associations that we say didn't happen by chance, we then say there are either statistically significant differences that occurred or statistically significant associations that occurred.